Gay on linear logic, session types, and deadlock freedom.
Okay, thank you. And thank you, organisers, for the invitation. This has been a really great week with a great collection of people. I've heard about some fascinating things that I'm sure I wouldn't have encountered otherwise. So this talk is going to combine a number of threads which are all more or less related to the themes of the workshop. So this is joint work with Ornella Dartha, who's one of my postdocs. It's also work in progress, so it's not complete, but it's progressing quite well, so I think I can give you a good impression of where it's all going. So the first thread of background to introduce is the Curie-Howard correspondence, also known as the propositions as types paradigm. So this is a cornerstone of theoretical computer science and semantics, and really the foundation of functional programming languages. And it's this idea of setting up a correspondence between programming language types and logical propositions. This extends to a correspondence between programs and proofs of the propositions. And then dynamics is introduced by the idea that evaluation of a program corresponds to proof normalization or cut elimination. So specifically in the core case, what this means is that a function type, A arrow B, the type of functions from data A to data B, is identified with the proof of A implies B. So computationally, we think of the function as a construction of a proof of B from a given proof of A. And the idea of this evaluation as proof normalization correspondence is that on the one hand, if you think about applying a function to a parameter in lambda calculus, the parameter gets substituted into the body of the function at all the places where it's used. And correspondingly, the idea of cut elimination is that logical cut is matching up A implies B with A, and you can think of it as applying a lemma. And cut elimination means that the lemma is inlined in the proof that's using it everywhere it occurs. And if you're not familiar with this area and want to learn more about it, there's a very nice article by Phil Wadlow, which was published in Communications of the ACM just a year ago, so I recommend that for background reading. So this is all very nice for functional programming, for sequential computation. And the question that's been around for quite a long time is what should the corresponding setup look like for concurrent programming? And way back in 1987, when Jean-Yves Girard introduced linear logic, the idea appeared and was explicitly suggested by Girard that linear logic, and in particular classical linear logic, should have something to do with concurrent computation and perhaps might form the basis for a nice Curie-Howard correspondence. And in the years following the introduction of linear logic, there was some work looking at this kind of connection, looking at pi calculus, looking at classical linear logic proofs, and certain correspondences were obtained. But I think it's fair to say that the results that were obtained didn't really catch on as the answer to the question of what is the Curie-Howard correspondence for concurrency, and didn't become a foundation for concurrent programming languages in the way that functional languages have their foundation in this logical correspondence. And then work in this direction sort of rather died down for a number of years. Meanwhile, the second thread of background I need to introduce is session types, which we've already heard about extensively from Nobuko at the beginning of the week. So session types were introduced by Kohei Honda around 1993, and then further developed with a number of co-workers. And the idea of session types is to use type theoretic techniques to describe the structure of communication in concurrent systems. And I'm vastly simplifying here and only showing you the very most basic cases of an input. So question mark means input. Input A, then B. This is a protocol which says first receive a message of type A and then continue to behave as protocol B. And dually, so the complementary description of what's happening at the other end of this communication channel, send a message of type A and then behave as B. And if these were to actually match up, the B here would have to be dualized in this way, which I didn't show. Now, there are other possibilities. So you can also represent branching, so protocols that have choices at certain points and can go in different directions. But I only need this much to explain. Now, Nobuko was talking about multi-party session types, which is how you describe collective communications among a number of concurrent agents. But here I'm just talking about what are known as binary session types. We're talking about the type of a protocol on one channel connecting two agents. And there's been a lot of work in session types over the last 20 years and more, and it's really developed into a large and active research area. And most of the programming language and theory conferences seem to have a couple of papers on session types these days. And then in 2010, Louis Kyrige and Frank Fenning published a paper in which they developed a Curry-Howard style correspondence between a particular form of linear logic. This was dual intuitionistic linear logic, as it's known, and session types for pi calculus. And this was really, I mean, when I read this paper, this absolutely impressed me. And this really seems to have a good claim to be Curry-Howard for concurrency. And part of the reason for saying it has a good claim to be the answer to Curry-Howard for concurrency is that just like the original functional Curry-Howard correspondence, it's proved possible to develop and extend it with a lot of extra features. So quantifiers, dependent types, logical modalities, other logical features which find corresponding analogues on the computational side. And what happens in this setup is that whereas in the original Curry-Howard correspondence, proof normalization or cut elimination corresponds to functional computation and an application in lambda calculus, here cut elimination corresponds to communication, sending and receiving a message matching up via a session type. And there's been a very productive series of work by Kyrige and Fenning and their co-workers over the last few years, really pushing this idea a long way. So just to give you a little flavor of how that works, the thing that was really amazing about this is that they identified the connectives of linear logic with the type constructors of session types in really quite a surprising way. So tensor corresponds to output. So the type A tensor B means this is the type of a communication channel on which you first send a message of type A and then continue to behave according to protocol B. And par, which is the De Morgan dual of tensor in classical linear logic, corresponds to input. So this is input a message of type A and then continue to behave as protocol B. And the remarkable thing that you can see just very formally in these rules is that the channel. So here you've got propositions annotated with proof terms. So this bit on the left is the process that receives on channel X, and what it receives is called Y, which is then bound. And then you continue to use the same channel, right? So you've got X here and X here, so that the channel is sort of threaded through the rule. And the same thing happens down here. You send value Y on X and then continue to use X. So the sort of combination of these two ideas that tensor is output and par is input, and that the way you do the term assignment in proofs is by threading the channel through, it made the whole thing work. And these were really quite surprising ideas. Okay, and this diagram is a not very beautiful attempt to illustrate what happens in cut elimination in this setup. So this is supposed to be the process that's inputting, and this is the process that's sending. And this line here is the connection between them, so the communication channel that connects them. And the reason why this line extends up here and extends up here just corresponds exactly to this threading of the channel. And this little bit of line is meant to be the message, and this is meant to be the message. And you'll notice that Another feature of this rule for output is that you've got two processes in parallel here. So vertical bar is parallel. The message that's being sent is created by a separate parallel component than the one that's running the rest of the protocol. And that's why there are these two boxes here. And what happens in a communication step is that the message gets matched up. This is where the message is consumed, and this is where it's produced. And then the continuation of the protocol gets matched up like that. So what happens here is that a cut on a more complex formula is replaced by two cuts on simpler formulae, and then inductively this enables cuts to eventually be eliminated. Right, crikey, I'm going to run out of time if I'm not careful. OK, so the third thread to introduce is the idea of analysing deadlocks in communicating systems. So deadlock is what happens when a concurrent system is unable to make progress because communications are blocking each other. So here are two archetypal examples of deadlock and non-deadlock. So what's happening here is that we've got two components in parallel. They're both using channel A and channel B. I don't care about the messages, just the channels. And here we've got input on A followed by output on B in parallel with output on A followed by input on B. And this is fine because the A's can match up and then the B's can match up. But underneath, we've got something where the output and input have been exchanged here. So both processes are waiting for an input, which is never going to happen because the corresponding output is behind the other input. So this is a deadlock, and this is OK. So the deadlock in this sense is something that can happen when you've got two processes sharing more than one channel, and it comes from a cyclic dependency. And one feature of this Curry-Howard setup with session types and linear logic is that the type system, as well as guaranteeing correct communication in the sense that messages are always of the expected type, it also guarantees deadlock freedom by imposing a very strong condition that you could only connect processes by a single channel, and that stops this situation arising. So this is the cut rule in classical linear logic, which enables you to plug two processes together on channels of dual types. So you can't make any cyclic connections. So you can't do anything like this, which excludes this deadlock situation and this situation which is actually not a deadlock. Okay. So in a sense, the deadlock freedom mechanism in the Currie and Fenning system is too strong. And in fact, if you just flip back here, it's important that you've got these two separate components within the output side, because that's what preserves this invariant that the connection structure of the processes is always a tree. OK. So to analyze deadlocks in a more sophisticated way, Naoki Kobayashi, in a whole series of work going back to 1997, has developed type systems based on the idea that there must be a consistent order on communication channels and the way they're used all the way through a system. And so if we look back at these two examples, the reason why this one is a deadlock is that you've got inconsistent orderings on the channels. But this one's OK because you can consistently say that A happens before B. So it's possible to set up a type system for pi calculus based on this idea, which guarantees deadlock freedom by type checking, but is more expressive than the Currie and Fenning system for session types. And this idea has also been formulated for a session type system by Luca Padovani, but without this logical correspondence. Right? These systems have been developed just as a type system for pi calculus without any logical idea. So to get to the point of what we have been working on, it is to combine all these ideas into a more expressive deadlock-free type system with a logical correspondence, thus extending the Currie-Howard setup for session types. And so what you really want to be able to do in order to form this kind of configuration is to generalize the cut rule that lets you plug on a single channel to this rule, which is called multi-cut, that lets you plug as many channels together as you want, as long as their types match up dually. But actually, you can shuffle things around in terms of which rules you have, and instead of introducing the multi-cut rule, we use mix and cycle. So mix just lets you put things side by side without connection, and cycle lets you form an internal connection. And between them, these rules imply multi-cut. So the idea of bringing in the Kobayashi-style type system is that every type, that is every proposition, gets tagged with a priority, which is a natural number. And then all the proof rules, as well as the usual hypotheses, are augmented with conditions on priorities. And the most important thing to look at is in the rules for input and output, where the priority that gets associated with the input or output connective has to be smaller, that is higher priority, than all the types that the process is using afterwards. Okay, so guarding corresponds to having a higher priority, and higher priority means smaller in this partial order. So something else that happens when you introduce the cycle rule into linear logic is that the distinction between tensor and par disappears. And that's why we end up with the same form of typing rule for both input and output. So we no longer need the fact that in the output rule, the message and the continuation are handled by separate parallel processes, because we've now got a more powerful way of guaranteeing deadlock freedom. But we choose not to just identify tensor and par. They're going to become isomorphic rather than identical. Okay, and in the cycle rule, in order to form this, this connection between two ports, as well as their types being dual, they have to have the same priority, which means eventually those two communication operations will be ready at the same time, and that's what lets them make progress. Okay, so I'll skip this because I'm running out of time. That's just a summary of the proof of deadlock freedom in the Kobayashi-style type systems. And so what we expect to do is, first of all, prove that our system derives everything that the original session-type linear logic system can. And then to take the Kobayashi-style reasoning from the deadlock-free type systems and repackage it into a proof of now cycle elimination rather than cut elimination for classical linear logic. And potential applications would be development of more expressive type systems for concurrent programming languages based on this linear logic correspondence. So, for example, Frank Fenning and his group have been working on implementations of concurrent programming languages with type systems based on the classical linear logic correspondence. And if we use the style of type system that we're developing, these languages would become more expressive. Okay, so that's it.
Thank you very much. Questions? Assumptions?
On a historical note, I thought
Yes.
you might have mentioned the interaction categories work, which you and I and
Oh, yes, right. Well,
type systems for deadlock freedom, and explicitly talked, maybe for the first time, talked about the multi-cut and the cycle rule. And,
yes, that's true. Yes, I should have.
you're one of the authors.
Yes, that's right. Nobuko mentioned it. So in fact, when people talk about multi-cut, they refer to that paper. And interestingly, so in some sense, that was going in the opposite direction, in that we were starting with the setting where anything goes and then refining the types to prevent cyclic connections, and then here we're starting with the setting where you can't have cyclic connections, and we're refining the types to allow them in safe situations. But yeah.
It would be interesting to compare where they end up, is it?
Well, I think so, and in fact, as far as I know, none of this stream of work about Currie, Howard, and session types has explored the categorical dimension yet. So there's an opportunity there to.
Was that Phil Wadler has always emphasised that I mean, you were mentioning his recent work, and I guess some of it is joined with you as well, but that it does relate strongly to the old proofs as processes stuff that you mentioned at the beginning. So I think it's completely true that didn't have much of an impact at the time, but in a sense, it's kind of been continued in this.
Yeah, I mean, it's sort of been brought into the picture.
The difference is your work and section type work is that same linear name is used many times, and your case is used only once, and I did closely related with your work, but section this series of work are different. One linear channel used many times because input and output, that is the difference. And but every work cited your work anyway, but I should say so. But
Fair, first.
You showed the rules, but I didn't quite see what stops you from forming the empty sequence.
Yeah, you can prove the empty sequence, yeah. I mean, the thing is, in this setting, you're more interested in the proofs rather than what's proved. But yeah, I mean, yes, you do end up being able to prove the empty sequence, yeah.
So why, I mean, why are you so interested in deadlock freedom? I mean, so there are two aspects to it, right? One is that you don't want the wrong messages to be sent.
Yes.
But there is the possibility that you don't get the message you're expecting to get.
mm-hmm.
Right?
This is right.
You are trying to enforce both here.
This is my question.
Right? I mean, why wouldn't you, like, I guess I'm asking, is there research which explores it rather than starting with linear logic, starting with compact closed categories, right? Where you'd get where you'd get, process, you'd get cycles of processes without having a global static priorities on channels.
Well, as I was saying, the categorical side of this line of work hasn't been explored yet. But the motivation was that so in the multi-party session types work that Nobuko was talking about, you get deadlock freedom because you start with this global type which you project everything from. If you just work with binary session types, so you're just looking at protocols on individual channels, you don't get deadlock freedom. So the fact that you get deadlock freedom from this Kairos and Fenning work was seen as a bonus because it's giving you a stronger correctness property. And so then there's the observation that, well, there's an even better system for deadlock freedom by Kobayashi. So can we combine that? That was the motivation.
I have a question. Yes, so you are treating global deadlock free or liveness because all system terminate, because Kobayashi's deadlock free means that some part you can execute, so it doesn't have to terminate, just progress.
Well, the Kairos Fenning system doesn't have recursion, so everything's terminating, and it's a question of whether it terminates successfully or whether it gets stuck along the way. So
it's normal pi calculus, right?
Yes, so what we're looking at is the Kobayashi typing idea applied to the Kairos and Fenning system without recursion
Which
at
means
the moment.
terminates.
Yeah.
Okay.
I mean, maybe it can be extended later.
Thank you very much.
Thank you.